I couldn't help continue working on problem 11, trying to get all the details under wraps. So I think I've solved it all now. So to finish it off, so I don't need to think about it anymore, I'll present my final answer. So we have a map of the complex, from the complex numbers into the projective 2D projective space, defined by Z is mapped to the same as with the Weierstrass P function, but here it's defined by not G. I'll just do that again. Where F equals cosecant squared. Now, we actually need to do it a little better, because when it's in the projective space, this is the affine part of it, so it should be 0.1. Now the derivative of this guy So to make the correct projective map, I think we should do it like this. Set maps into, and then we multiply them all by sine to the third. So this is, the first one is cosine sine. Point minus 2 cosine. Point sinus sine to the third. And now it's obvious that null works. We can map null to 0.1.0. So now we have a map from so this will just be the closure of it. But let's see if it really is the closure of the curve in the projective space. And to that end, we write up the equation. We denote this as x point y, then y squared equals 4x to the third, or just to the second, times x minus 1. So will all points of this curve be hit by this function? And now I've written it as an affine equation. We should write it as a projective equation as well. 4x to the third minus 4x plus, no, 4x to the third minus 4x to the second z minus y squared z. So that's the projective closure. So we can hit naught by using pi half. Yeah, so maybe it is. Now, the first thing is when we plot the real part of the curve, we get naught, and then at unity we have the two branches going up here. So this really looks like a singular point. All the coefficients are real, and it's a singular affine point, so a real affine point. So it's reasonable to believe that it is But let's seriously find all the singular points. So let's write smooth points. So to do that, we must solve the derivative of the equation with respect to x, y, z. 12x squared minus 8x squared. Now 8x 4x times x minus 3x minus 3x minus 2. There we go. And derivative with respect to y and with respect to z. So, common solutions of these three equations. This one simply gives x or y vanishes, this or, and this one gives 2x plus iy, 2x minus iy. So let's see. 1. If we go up to this guy and take y vanishing, then we get x vanishes whichever of these holds. So that's the point we already suspected. So that was y. The next one is z vanishes. That's the line at infinity. What happens there? Well, one of these must hold. So if we have x vanishing, then y will vanish as well. So we have 3x minus 2 vanishes. So x equals minus 2/3. And this gives a value for y. For third. Now this was surprising. I'll just check that once again. Draw back to the third minus. Yeah, it's wrong. It should, of course, be times z. So it's 2z inside this parenthesis. Now where are we? So all this is wrong. So if z vanishes, then x vanishes as well. Of course, the other thing, getting a number, was insane. And then y values as well. Contradiction. So we only have the one singular point. After doing all this work, I wondered, why am I so interested in the singular points? And then it dawned upon me, because when we add this, if we should add a singular point to itself, it would be difficult to find a tangent at the point. At this point, we have two branches not two branches, but two different parts of the curve intersecting. So there are two places. And they have different tangents. So adding the point to itself is impossible. We could add the places, but that's not what we are doing here. Now, so we have to exclude this point. So the whole projective curve except the singular point is what we are looking at. We should know what the singular point is. And it's easy to see when z tends to high imaginary or large negative imaginary, then this will turn towards zero, the center, so it's dense around the point. So it's really a singular point we have to exclude. Now, that was the map and this guy, and then we have to work out addition. So on the complex plane, we consider a strip here. And that's because this function, where is the cursor? This function is periodic with period 2 pi. No, that's interesting. Is it period pi or 2 pi? I thought because we squared, it was only with period pi. Yes, that's it, with period pi. So everything we get from any strip, so it's a periodic function with period pi. And we have addition in C here. And we want to extend that addition. And naught, of course, maps to the point of infinity. So the first thing they do in the book is to take the, to show the point at infinity is the inverse, is the neutral element. We'll skip that. And then that the inverse of a point here, the one coming from the opposite, I will just do that, which that is. So now we use the additive notation, so it's minus x point y minus, and we'll just use this guy because we already have taken care of the neutral element. And that we get that from taking the opposite z value. and it's obvious that, that this guy is the same, and because of the denominator, this changes sign. So that's the inverse element. Next, we have to prove that the sum of two elements is given by the usual geometric procedure. And I will just repeat the derivation from the book, from the section. So we will find the solutions or the intersections of a line with the curve. So we solve the equation y, that's, I think I called it g, didn't I? No, f. And we enter the function here, or put this on the other side, and define a new function. What have we come to? H. Put this on to the right side, 2 cosine z divided by sine to the third plus m second plus b. So that's the function, and we shall prove that the sum of the zeros in this. So we have 3 zeros. We'll come to that in a moment. And we shall prove that the sum of these 3 zeros vanish. I didn't draw them correctly, of course. The first thing is that it's the sum of the poles and the zeros. We get that by taking the integral of its derivative divided by h of z, and then around a curve that goes, for instance, like this. That should have been done more precisely. So we go down along this, and then up here, and then back here. And we do that some large number m tending to infinity, and here t plus im. Now this guy tends to naught, as the imaginary part of z tends to infinity and minus infinity, and does so exponentially, or was it sine to the second exponentially? Yeah. So this is finite, and since it's periodic, down and up here, they are equal in value, so that cancels. And since this has finite length and it tends to the value tends to naught, this part will, I don't know if it cancels, but it'll definitely tend to 0. So that means that this integral vanishes. Therefore, the number of poles equals number of zeros. And we have a pole at naught of order 3, so we have 3 zeros. And the pole being at 0 is very nice, because then this one will just give the sum of the zeros. Now, the same argument goes with these parts, and then going down here and up here, it's the same except for z. That was what I missed in my video. So what we will get is that this difference between the two real values, so it's pi. Oh, I just made another mistake. It's 1 divided by 2 pi I. There we go. So now what was I saying? Oh yes, this equals just and this path up here, let's call it gamma. And I have prepared this, so I'll immediately write it as t divided by 1 minus t squared, where t goes from -1 to unity. Let's call it curve 1. Gamma 1 of pi Now, the reason I define gamma like this is that we make a new path, gamma 2 being gamma 1 of being h of gamma 1 of t. And as t tends toward -1, gamma will tend to -infinity, so this will tend to b. And as it tends to unity, the same thing happens. So it's actually a loop. And the next thing is that it's differentiable from the right here and from the left here, because this tends to infinity so quickly that the derivative vanishes. And that means that we can be sure that this integral actually converges. If we had it from -infinity to infinity, I couldn't be quite sure that it would converge. So we have a loop, and it's a differentiable curve, and that means that this is the, we'll just write it more So this integral is the number of times we loop around naught in going from B to B. So that gives 2n pi I, where n is the number of clockwise turning arounds. And this gives n pi. So I haven't proven that the sum of the zeros I've made a mistake here, because the zeros of this one, oh yeah, there's zeros everywhere, but I've just proven that they lay that the sum lies in this it's a multiplum of the period, so that means that they can be translated into the same. And that was what I did without really taking responsibility of when I could do that. The zeros will, of course, there will be 3 zeros in this slice, maybe on the line here, of course, but the sum of them will lie in the lattice. So it might be 3 zeros down here, so that the sum was out here, or rather here. So never mind, you can figure that out, it's no problem. So that means that we have proven the addition formula. And now what more should we do? The rest was solved. So it is actually possible to do this with the Weierstrass P function, with the cosecant squared, and as we did in exercise 10, 1 divided by z squared, and then go through all the motions and everything comes out nicely. So that was just to so that I could finish cycle on this, end it. I've done it, I've proven I can do it, and now I don't need to think more about it.